Hi everyone, my name is Andrei Ivanovich, and today I'll be talking to you about our work on coordinated motion planning via imitation learning. Here, we have a scenario where two AVs are passing through an intersection to reach predefined goals. Currently, many motion planners treat other AVs as independent agents similar to how they view human agents, and plan to avoid their futures without exploring the potential for collaboration. If the two AVs can share information with one another using vehicle-to-vehicle communication, then they may be able to design a joint motion plan to yield smoother and safer interactions on the road, especially in complex scenarios such as four-way intersections. Our proposed process for developing coordinated motion plans begins by assuming temporary centralized control over both of the vehicles in the scene and establishing a means of sharing information with one another. The two vehicles then jointly forecast their potential future trajectories and finally generate safe, coordinated motion plans that deliver each AV to their goal by using the expert-like trajectories that were forecasted in the prior step. There are two key components to our proposed pipeline: the trajectory forecaster, which uses R2P2's proposed model, and the motion planner. By using the trajectory forecaster, the coordinated motion planner is able to search for human-like trajectories by minimizing a non-convex cost function using gradient descent. Formally, the non-convex cost function being minimized is the final displacement error between the final state of our model's produced expert-like trajectory, denoted by g sub pi of z, and the final state of the ground truth trajectory, denoted by y sub t, which is the goal corresponding to vehicle I. An optimal z star results in each AV reaching their goals without any unsafe interactions between each other. We experimentally verified our method's performance on a didactic dataset. The dataset is trimodal, representing an intersection where a vehicle can either turn left, turn right, or continue straight. Two AVs are placed in the scene facing each other in two different lanes. Expert ground truth trajectories were generated for each of the three modes with constant velocities. Scene context consisted of each car's states for the previous 5 time steps as well as a semantic bird's-eye view observation of the intersection. First, we tested our model's ability to accurately forecast future trajectories. The ground truth futures are denoted in darker colors and the predictions in lighter ones. We can see that the lighter predictions closely align with the darker ground truth as expected. Then, we tested our method's ability to take into account contextual information. By using two different types of intersections, we wanted to verify that our model was able to accurately output the futures corresponding to that intersection type. These images highlight the model's ability to incorporate scene context into its predictions. The two figures on this slide show the model's ability to optimize over a simple, base distribution to find human-like trajectories that best accomplish each AV's goal, represented as red points in both images. On the left, we have a visualization of the optimization process, where lighter paths indicate planned joint paths earlier in the process, and darker ones indicate later ones. The solid green line is the optimal path at the end of optimization. On the right image, the optimal joint path is overlaid onto our test dataset, shown in gray. As we can see, the resulting optimal path very closely imitates the gray ground truth expert trajectories. Thank you for listening.